the cloud. All right, good afternoon. Uh, Welcome to another lecture 8 of our quantum computer course. So today we're going to talk about quantum algorithms, and we will discuss as a particular example this quantum teleportation algorithm. Right, so as usual, as before, we start with importing some libraries. Yeah, so quantum algorithms. A quantum algorithm is the uh, last thing that we need to realize quantum computing. Okay, so we already discussed several things, including a qubit and a quantum superposition, right? So a qubit is a quantum system that can exist in either quantum state or in the superposition of both. Okay, so we require a qubit to be able to exist in a quantum superposition. What it means that even though the qubits being measured, we always find it in either state 0 or 1, if you measure it in the 0-1 basis. Yet we have to assume that this qubit is given in a superposition, in the combination of these two states, like simultaneously before our measurement. And this state is coherent, which means that it can interact with say with another state of another qubit. And the word coherent here means that it can form interference. Okay, this interference of the states of the same qubit and the states of different qubits can lead to constructive and destructive interference, just like waves on the surface of water, right? When we if we coherently create two kind of cylindrical waves going radially, right, from, for example, we drop a piece of a rock to the pond, right? We create this concentric wave. So if you create two of them, there are areas where the waves come in phase and kind of amplify each other, right? The response is greater than the response of or amplitude of one wave. And there are other areas where these waves cancel down each other. So no wave in there. So constructive and destructive interference. So something very similar happens in the quantum computers. We also require the qubits exist in the entangled state. Okay, so these qubits not just interact; they form entangled states. Entanglement. This is the way we generalize a system. We construct a system like adding more qubits to the quantum computer and forming entanglement, mixing these states of all these qubits together, we form much higher dimensions, right? So if we add qubits more and more to the quantum computer, this Hilbert space dimension scales as 2 to the power of n, where n is the number of qubits. And if for just 2 qubits, for example, this number is 4, so not very impressive, but for 100 qubits, it is 2 to the power of 100, which is a colossal number. It's a huge, great number. Today we have computers with 1,000 qubits, so it's a number that we cannot even imagine. Okay, so this is how this principle of quantum parallelism works. Quantum interference, as I said, all these terms, all these basis states must be able to interfere. So, and finally, how we get like useful information from all these great number of states, right? This is achieved through the principle of quantum algorithm. So the idea of a quantum algorithm, just like for waves on a surface of water, to make interfere constructively partial waves in the computer constructively for a correct answer, okay, and destructively for all other wrong answers. Okay, so quantum algorithm is a procedure we operate with this quantum circuit to make it interfere constructively for an answer we after. All right. So this is a schematic presentation of a generic quantum circuit, quantum algorithm. Different algorithms, of course, work different way. Here I try to illustrate kind of the principle of kind of the vast majority of these algorithms. So here we see m qubits, m plus 1, right, from 0 up to m plus 1 qubits. These qubits physically, in terms of IBM quantum computers, these qubits, they constructed in form of some quantum circuits. Okay, they are standing elements on a chip. Okay. In contrast to classical computers, electronic computers, where we have these currents that move from one element to another element. In other words, it is spatial computing, right? The computation happens as the current flows from one point to another. Quantum computer, especially these IBM quantum computers, they are temporal computers, meaning that these qubits are placed on the specific places over the chip. And what we do to achieve these gates, we send some kind of pulses, okay, that control these qubits. So it's a temporal computing. Okay, so we have m or m plus 1 qubits. They are entangled. Okay, so they can be entangled, meaning that these qubits form some sort of a topological pattern with some interconnects. Okay, and we can control these interconnections between different qubits to form different entanglements between all these qubits. So typically, the first operation is to create the superposition, apply the superposition of all these qubits, applying this layer of H gate, Hadamard gate, right? So after this Hadamard gate, all these qubits are in the perfect superposition. And then we have another layer of Hadamard gates in the output that close these interferences. Okay, the close, we say that this first layer opens interference, the last layer closes the interference between these qubits. And the magic happens in between these two layers. Okay, it's just like, for example, a piece of glass where light enters, can reflect, can transmit, and partial waves reflect and interfere to form, for example, some sort of resonance. Okay, similar things happens here, and then we apply some sort of a function, okay, that can control these particular qubits in some particular way, it's a desired way. Okay, so this function can be called an oracle in some algorithms, and we can control this function, this oracle, using classical stimuli. Okay, so we can program it. Right, so this is the general picture of the quantum algorithm. Give me a second, I will be right back. Yeah, so just maybe give you one example of how this can work. So for example, this Grover search algorithm, right? This Grover's algorithm claims that you can do a search in a non-structurized massive of data much faster, like exponentially faster than in the classical computing. So what you do, you have this sort of m qubits, and 2 to the power of m represents a huge number of terms, of eigenstates, right? So you can encode or map all these elements in your massive, in your array of elements, to a different eigenstate. Okay. So then, if you can do so, what you need to program. Say, I want to search for element 1200 something, right? What you do, you program this function that will form the constructive interference in the output for that particular element that you after. And of course, any algorithm ends by an array of measurement. Okay, so you measure this system, and as the output you get this array of classical bits, the result of your measurement. All right, so let us discuss the first and maybe the easiest quantum algorithm, which is called quantum teleportation algorithm. And we start from the importance of this algorithm. Okay. So in quantum, we have this non-cloning theorem. Okay, so non-cloning theorem basically a statement that we cannot copy a quantum state. Okay, so imagine a qubit existing in some particular quantum state. We can prepare the state, but if I want to measure this state and to create another one, my measurement destroys this quantum state. Okay, so I always find this qubit in a 0 or 1, but not in the quantum state. I cannot measure the quantum state itself. And for this reason, I cannot clone this quantum state. Now the question is, how can I copy the quantum state from one qubit to another qubit? That can be like physically another qubit and can be located somewhere very far away from the first one. So how can I transfer this quantum state from one qubit to another qubit without measuring it, without destroying this quantum state? Okay, and it turns out that that's possible, and we do so using this quantum teleportation. So let me give you a simple example of quantum teleportation, and that uses this principle of shared randomness. Okay, so let us imagine two guys, Alice and Bob. Okay, A and B, Alice and Bob, and Alice and Bob can share a pair of qubits that are entangled. Okay, and Alice wants to transfer the quantum state from her qubit to Bob's qubit. Okay, so and here I put this simplest quantum algorithm, quantum teleportation algorithm kind of logic, right? The procedure. To describe all these, I decided to use this SymPy physics quantum. It is a Python library that allows to work with symbolic quantum computations. Okay, in order to demonstrate how it works, unfortunately, I cannot use Qiskit because Qiskit works with a specific quantum state. But I want to demonstrate this principle in general. So if you're interested, feel free to Google this SymPy physics quantum. It's a very large and developed library, not only for quantum computation, but for a lot of physics computation. This very nice and very useful approach, very useful platform and library. For us, as I said, it's important that it allows to work with symbolic quantum states. So here, for example, I create two qubits in state, one qubit in state A. Okay, so it's a Alice qubit, and another qubit in state B. It is a Bob qubit. So Alice has a qubit in a general quantum state, right? Alpha 0 plus beta 1. So it's superposition of 0 and 1 states with different alpha and beta, and alpha and beta can be complex. Okay, so this is also important because we're transferring the state that is described by complex valued numbers. And Bob, by default, gets this qubit in the state 0. Okay, so the entire system the both of them described by they described by this the state like this, right? So tensor product of these two states. Okay, so the first one here is a bob. So right, we count the qubits from right to left. So these two are Alice's states, and this 0 is the bob state. So it's just the scalar product of, not scalar, but tensor product of these two states. Okay, so nothing happened so far. It's just the way how we describe the entire state of the system. So what we do first, we make this two qubits, Alice's cube and Bob's qubit, entangled. Okay, so in order to do so, we apply the C0 gate that we discussed some time ago. Right. So this lowest qubit is Alice's qubit. Okay, so it's a little bit different notation comparing to the Qiskit, where the first qubit starts from the top and goes down as the number of qubit grows. Here in this platform, the first qubit starts from the bottom, and then adding more qubits goes up. So this lowest one is the Alice's qubit, which is control, and the target qubit is Bob, right? So we form the quantum superposition, the entanglement of these two qubits, and the resulting state is like this. Okay, why? Because if my control state is 0, then my target leaves unchanged, right? When my target is 1, the target flips, changes in this case from 0 to 1. So this is the quantum state in the output from this two qubit operation. So now you see that this state is entangled. Indeed, you cannot present this product, this state as a product of two. Okay, but this is not a Bell state, because for a Bell state we had 1 over square root of 2 here, 1 over square root of 2 here. Now this alpha and beta assumed to be arbitrary. Okay. So before that, if for example Alice now measures her qubit in the 0-1 basis, okay, she will find out that qubit in the state 0, okay, and then she immediately knows that Bob's qubit is prepared in the 0 state. If she finds her qubit in state 1, then she immediately knows that Bob's qubit also in the state 1. So no magic so far. But instead of measuring this Alice's qubit in the 0 or 1, she can change the basis to plus minus basis, okay, applying this Hadamard gate. Okay, you remember Hadamard gate creates the superposition of the states. So if if Alice applies this Hadamard gate to her qubit, the final quantum state of the entire system will be given by this expression. Okay, so now these two terms are in the superposition of 4. Okay, so with different amplitudes. So Now, if Alice measures her qubit in the state 0, in the basis 0 or 1, okay, 0 or 1, and let's assume that Alice finds her qubit in the state 0. So it says this term and this term, okay, alpha 0, 0, beta 1, 0. So if she finds her qubit in the state 0, she immediately knows that these two disappear, okay, and Bob's qubit is in alpha 0 plus beta 1. This is exactly the quantum state she wants to teleport, okay. Alpha and beta are arbitrary. It works for any alpha and beta, including complex value. So she immediately concludes that Bob's receives the correct quantum state, the state she needed to teleport. Okay. Similarly, if she finds her qubit in the state 1, these two disappear, and the Bob's qubit gets alpha 0 minus beta 1. So this is almost the quantum state she wants to teleport up to this minus sign, right? So what she then does, she takes a classical like phone and calls Bob, telling him you need to apply the gate X to your qubit. And if he applies this gate X to his qubit, he flips this sign from -1 to 1 and restores the correct quantum state. Okay, so this quantum teleportation works like this. You do this quantum measurement, and depending on the result, Alice sends either 0 or 1, depending on whether Bob needs to apply or not this X gate. So the conclusion of this is the fact that you cannot send this state like faster than the classical communication channel allows you to do so. So you still need to tell Bob to whether apply or not this X gate to his qubit. But anyway, you or Alice, in this case, Alice can teleport the quantum state to Bob without destroying this state. Well, she measures her qubit on her side. She destroys the quantum state, but this collapse of the quantum state on her side results in a kind of the teleportation or cloning of this quantum state, exactly the same quantum state on the Bob side. Okay, so this is how the simplest quantum teleportation algorithm works, and this is the essence of this shared randomness. Okay, this shared randomness simply means these results. Okay, you never predict, or Alice never can say for sure which state she will get and which quantum state she will send to Bob. Okay, so it's a random process, and you need to communicate. Alice needs to communicate with Bob to restore the actual quantum state. Shared randomness. Okay. So now let us discuss a more practical approach to quantum teleportation. Okay. And before that, let me tell you that some of the quantum cryptography protocols, okay, so the security protocols use this approach of entanglement for quantum teleportation. So this let me see. Yeah, so this algorithm is applied in real applications already. So more practical approach to quantum teleportation. So this approach requires at least 3 qubits. Okay, so we create a circuit with 3 quantum bits and 3 classical bits. So I assume that my qubits initially are in the all zero state. So this is my initial state of the system, the quantum state. Then I apply, then I change the state I want to teleport. Okay, so this qubit 0 is prepared to the state 1, and this state 1 I want to teleport. This gate can be any other gate that prepares this this quantum state in a particular state that I want to teleport. I forgot to mention that I assume that Alice has this qubit 1 and 2, so these 2 qubits belong to Alice, and the third one belongs to Bob. Okay, and Alice wants to teleport the state from qubit 0 to qubit 2 that belongs to Bob. So she prepares the state to be teleported. In this simplest case, it's a state 1. And the state simulation gives me this state. So it's indeed 1 in the qubit 0. So next, we prepare an entanglement between the second qubit that belongs to Alice and third qubit that belongs to Bob. Okay, so we apply this Bell state creation, this 2 qubit golden circuit, right, to the pair of Alice and Bob qubits. All right. So now my state becomes this one. So indeed, this is the entangled state. Next, Alice needs to measure both her qubits in the Bell basis. So she applies this Bell circuit in the reversed form, right, in the reversed order, to create to go to the Bell basis. Okay, and yeah, so the total state of my system becomes like the combination of these vectors. And now in this Bell basis, she measures her first and second qubit. So these are the measurements. Okay. Bob's qubit is not measured yet. Okay. So finally, depending on these results of this measurement, she calls Bob and tell him what operation he needs to apply to his qubit. Okay, so in this 3-qubit realization, these operations must be Z and X gates applied to the Bob's qubit. So this double line represents again the classical line. Okay, so it's a control Z and control X gates, but controlled by classical bit. Okay, 0 or 1 defines whether this gate applied or not to the Bob's qubit. Okay, so I cannot calculate now this vector of the Bob's qubit because my circuit contains this measurement, right? So it's classical operation, and I cannot represent this in the quantum way, but I can do the simulation of this measurement using this Qiskit-Ayer simulator, like we did before, and this is the result of the measurement. Okay, so now this result of the measurement applies to this control Z and control X gates that apply to the Bob's qubit. Okay, so this information transfers to the kind of Bob's qubit and restores the quantum state that we need to transfer. And in order to demonstrate that, we measure the Bob's qubit, placing this final measurement gate, and simulate this circuit classically, and get this result. So indeed, all these measurements are found in a state for the Bob's qubit to be in state 1. You see this, all states are in the state 1. If I do the same procedure for the state, for example, 0, if I apply another, if I start over and apply second X gate, since any gate is unitary, right? Applying this gate twice simply restores the initial state. So in this case, it will be state 0. State 0 indeed. And then I do this procedure once again. And and finally, the result, is the state 0. In a general case, it will be something else with different this counts for different states. Yes, but to demonstrate this applicability of this approach for a general arbitrary system, we can again use this SymPy quantum library. Okay, just like before, I start from this state. So my first qubit, the one that belongs to Alice, right, is in the state alpha 0 plus beta 1. So it's a general state. and then second Alice qubit is in state 0, and Bob's qubit in state 0. Going similar way, starting from this Bell circuit, right? We create the superposition. Then applying this Bell circuit in a reversed way to the Alice's qubits, we get this result, right? So the Alice's qubit is the lowest one. Then the second one is also Alice's qubit. And she entangles this qubit with the Bob's qubit on the top here, right? So finally, we get this like big state of all these combinations, and Alice measures her qubits in the new basis, and here we return the result. Okay, so here we get these two states belong to Alice. Okay, so we not interested in these states. These two are of our interest. This alpha 1 plus beta 0. So this is the state that belongs to Bob. Okay, this is not the state that we after, right? Because this is alpha 1 plus beta 0. It's supposed to be alpha 0 plus beta 1. So we need to apply this X gate to restore this phase, right? To basically flip the states. We do so, and finally get this result. So it's two bulky terms, but what is important is this alpha 0 plus beta 1. So indeed, we can teleport, or Alice can teleport the quantum state from her place to Bob's place. Yeah, so this is basically it for today. Do you have any questions? Right. If not, then thank you very much. This lecture will be uploaded for your use. Stop recording.